Swayam Prabha. Digital India. Educated India.
Okay, in this lecture I'll be talking about rate of batch drying. Before we discuss what is rate of batch drying, the question of drying operation, the design question is how much time is required for a drying operation if you specify the drying material that you want to dry and the drying conditions, like how much air you're going to send, what the temperature of the air, what's the humidity. So those are all drying conditions. So for a given drying condition, how much time is required to dry a solid from one moisture level to another moisture level. So that is the design question that we want to pose. Time required to dry a solid from one moisture level to another for a given drying conditions. So this is basically the design question that we wanted to pose. Now, drying is a little bit difficult to theoretically predict. Okay, this is because the substance, that the solid substance that we want to dry could be made up of different kinds of material. Okay, it can be organic, it can be inorganic. The microstructure in the solid can be very different, and what is the chemical makeup of the solid is different, and how the composition of this material interacts with water is also very different. So because of this, we don't have a very good theoretical understanding of how to predict drying kinetics. Okay, even though it's very important and it's very useful for our day-to-day life as well as from an industrial point of view, but our knowledge of how much moisture a solid can contain and what is the drying kinetics, these are all the things that we are not able to predict theoretically. Okay, we don't have a thermodynamic model to predict these things because of the complexity of the question. So then how do we solve this problem? Well, what we do is we try to conduct a lab test for drying. Okay, let's say for an industrial scale you have a large amount of material you want to dry. What you do, you take that material in a very small quantity and then you subject this to a lab drying test under a very similar condition that you want in an industrial setting. Okay, by matching the drying conditions in the lab scale and in industrial scale and using a very small amount of drying material, you can look at what rate the moisture is removed from this material. Okay, so this is basically a lab test, lab drying test, and then based on this lab drying test we can infer some information and we can use this information to scale up and predict what's the actual time required for a large industrial scale drying operation. Okay, so that's the strategy we are going to use. This strategy is very experimental oriented. Okay, so there's no way we can use a lot of theory for this case, but we are going to use experimental lab scale testing. Okay, and this testing can be done for any material. You change the material tomorrow, you can do a similar kind of drying test for that material. Let's say you want to dry cloth versus you want to dry a slurry of some suspension. So change the drying material and do that same test, and then you get a different kinds of drying curve because the nature of material is different. Okay, so this is very much dependent on the drying test information. So how do we do this drying test? So when we look at this drying test, the need for this is we don't have a good theory to find the moisture content in a material. This is because the solid material can be amorphous. It may have microstructures that are very different from each other, chemical compositions, interaction with water. So these are highly dependent on the material in question. Okay, so because of this, having a theoretical description of drying rate is very challenging. So for to avoid this difficulty, we try to do a drying test. So when we do drying test, so we look at industrial scale drying, and then we have a lab scale drying. So in the industrial scale, we basically have to manage very large amount of material, okay, large quantities. Whereas in the lab scale, we will take a very small sample, very small sized sample, and then drying conditions. When I say drying conditions, I mean what is the air temperature that I am going to circulate, what is the humidity, what is the flow velocity, etc., etc. Okay, so these are all drying conditions, and I want to maintain the same condition in the lab scale drying also. So by taking a very small sample and then you put the sample in a weighing balance, and then you subject to this drying conditions, that is, you are going to circulate air at a particular temperature, velocity and humidity, and then you monitor the weight of the sample as a function of time. Okay, so you have time here, and then you say weight of the sample. Okay, so you look at the time, various time interval here, and then correspondingly you are going to look at what is the weight of the sample. And let's say you also know what is the dry mass of the solid. Okay, in the absence of any moisture, you can get that by putting the sample in a furnace and heating to a very high temperature, also making sure that the material does not decompose. So when you do that, pretty much all the moisture will be gone. Okay, and then you take that as a dry mass or bone weight. Okay, bone, it's called bone dry solid without any moisture. You get that dry solid mass, and when you take the difference between this weight of the sample and the dry weight, that will tell you how much amount of water is present in this material. Okay, so you can basically calculate mass of water by looking at mass of this material minus mass of the dry material. Okay, this is something you can get for all the time interval. Okay, so then I can define moisture as m minus md over mass of dry. Okay, this is our moisture. Moisture is defined as kilogram of water over kilogram of dry material. Okay, so I can find out this moisture as a function of time. Okay, so the outcome of this drying test would be a drying curve where I draw the moisture x as a function of time, and you will see something like okay, so this is kilogram of water over kilogram of dry solid. So this is time, maybe in seconds or hour, whatever it is, depending upon nature. Now this is a laboratory lab scale testing of drying conditions. So as long as you maintain the same kind of drying condition that you expect for industrial scale drying, this curve is very useful. You can always say that, let's say you start with the, in the industrial scale, let's say you want to start with the material of this moisture content, and then you want to dry it to this this particular level, and the time taken between this to this basically tells you the drying time. Okay, so accuracy of this method would be how accurately you reproduce the drying condition that you want in the industrial scale versus what you do in the lab scale. Okay, as long as you match the drying conditions the same material should be used, which is representative of the larger material that you want to use in industrial scale. So if you match that, you can readily use this drying curve as a basically to answer this question that I posed, that what is the time required for this solid material to dry from one moisture level x1 to another moisture level x2. Okay, so that the problem is solved. But however, many times we may want to change the drying condition a little bit. Okay, we may want to change the air velocity, we may want to change the temperature, we may want to change the humidity, etc., etc. And we want to ask how much information I can draw from this specific drying condition, and then maybe extrapolate to some other drying conditions possibly. Okay, so in order to do that, we are going to process this data. This is a raw data. We are going to process this raw data and plot it slightly differently. What we can do is, I can find the rate of water evaporated, that is basically mass transfer flux from the solid from this curve, okay, and I can plot that as a function of moisture content itself. So from this raw data, I will define a quantity called the evaporation rate or drying rate, with the symbol n, defined as minus SS by A delta theta into delta x. So delta x is the change in the change in the moisture content over a small time delta theta. Okay, so delta theta is the time interval. I am taking a small time interval, and delta x is the change in the moisture content over the time delta theta, and S here is the mass of dry solid, and A here is the area of the wet solid available initially before the drying happened. Whatever the amount of area, wet solid area that we have, that is taken as the area here. So you can see this S times delta x. What is that? What is S times delta x here? How much amount of water? What happened to water? Evaporate. So this basically tells you S times delta x tells you the total mass of water that got evaporated over a period of time delta t. Why I have to multiply by S is that delta x is defined per unit mass of dry solid. If I know total mass of the dry solid, which is S times delta x tells me the total quantity of water evaporated over a period of time delta theta, and then per unit area also, because we want to talk about rate in terms of per unit area fluxes. Okay, so this is a mass transfer flux. So kilogram of water evaporated per unit time and per unit area, that is the definition of flux. That's how N is defined, and I put a minus sign here because delta x is negative, because water is getting lost. But we wanted to kind of change that sign so that we don't have to worry about this negative sign, because we know with respect to solid the water is getting evaporated. Okay, so that minus sign is to make sure that N is in positive quantities, even though water is being lost from the solid. From our original mass transfer equations, we wanted N to be negative to say that water is lost or gained. Okay, so here for conventional reasons, N is written in this particular definition, and N will be positive if the solid is losing moisture. Okay, and area A is also very important, because as the material dries, the total area available for drying will also change, because initially the moisture will cover the solid, the area is a little different. As it dries, the amount of water content decreases, the area may also change, but for now we will say this area is the initial area before you start the drying. Okay, so now what we can do, I can go to different x values on the y axis, and I can draw a slope of these line over many x values. Okay, so that slope is nothing but delta x by delta theta, and this SS by A, that is a constant. So what I can do is, using this raw data at a different moisture content X, I can find the slope. From the slope I can find the drying rate. Okay, so thereby I can eliminate time. I can relate only the moisture content and the rate of drying. Okay, so when we do that, we can see that some nice features emerges from this simple raw data. So the figure on the left is the drying curve, that is X is plotted, moisture is plotted as a function of time, and then it starts at some initial weight and then it slowly dries. Okay. On the right hand side, what I do is, along this curve I choose different X values. For each of those X values I find the slope of this curve. Using that slope I calculate drying rate N, and then I correlate that N versus X. Okay, you can see the time is gone here, time is not relevant here, time is implicit here. Okay, as X decreases, so X is something that starts from here and then it decreases in this way during the drying process. So time has to be read in this way. Okay, and then we see that at each of those moisture content, what is the drying rate N is. If you look at this, you see that the so simple looking drying curve here is manifesting itself into some nice features. Okay, when you plot it in the rate of in terms of drying rate. Okay, so this particular curve is called drying rate curve. So what you see here is, you see there is a particular region where there is a particular range of moisture where this N is constant. That means the evaporation rate is constant over a range of moisture content. Okay, so the solid is drying at a constant flux, constant rate of drying. That is one feature you see. And then there is another level between here to here, that the drying rate decreases with the moisture content. Okay, so these are very much a characteristic feature of this drying curve itself. Okay, so this is a drying curve, this is a drying rate curve. So we may ask, okay, why is that drying rate is constant over a certain moisture content, and then after that why the rate is decreasing? Okay, so what happens is, suppose if you think about a solid containing moisture forming a thin film on the surface. Okay, so then I am talking about unbound moisture that is present on the surface covering the solid, and this unbound moisture would exert a vapor pressure equivalent to that of the pure water, okay, at the same temperature. Now if you consider that part, okay, a wet solid having a thin film of water around it, and then you're looking at how this would dry and what is the rate of drying can be written. Okay, so we will say that for a wet solid containing unbound moisture covering the solid as a thin film. Okay, so in this case, if you write what is the rate of mass transfer, we can write this is sometime ky times ys minus y. Okay, if I want to theoretically calculate the mass transfer rate, I would apply the convective mass transfer law. I write some mass transfer coefficient. This mass transfer coefficient will depend on the drying condition. What is the rate at which the gas is flowing, what is the drying temperature, what is the nature of the gas, etc., etc. Okay, so it's something that you can get from some correlations based on the flow conditions. Then this Ys here is called the saturation humidity of the air. This is saturation humidity of air corresponding to liquid temperature. Whereas this Y here is the actual humidity of the air coming over. Humidity of drying air. And this is the mass transfer, gas phase mass transfer coefficient. So why is that I am writing mass transfer rate with respect to the gas, not with respect to the liquid? So this is a solid having water on the surface forming a thin film. So for this, water is like a reservoir, okay, water is abundantly available. So the rate of mass transfer now is based on at what rate the air can sweep away the evaporated water. So the rate of mass transfer will be largely controlled by the gas phase, in this case the air, okay. So that's why I write this in terms of mass transfer coefficient of the gas phase, and then the driving force for the mass transfer, which is the saturation humidity minus the actual humidity of the air. Now the saturation humidity Ys will depend on what is the temperature on the surface of the liquid film. Now if you think about this process, drying, I have been talking about only mass transfer, but actually there is a heat transfer also happening, okay. The air is supplying some heat to the liquid that is used for evaporation of this water, okay. There is a heat transfer and then there is a mass transfer, both are happening simultaneously, okay. So when this rate of heat transfer mass transfer balances, the liquid attain a particular temperature, surface temperature Ts, okay, which will be constant. At that constant temperature, what is the saturation humidity? That is what Ys is, okay. Now since I have not talked about humidification and dehumidification yet, we will say that this relative the saturation humidity is something that is something available the moment you know what is the liquid surface temperature, okay. You can use psychrometric chart to get that, okay. So in some of the example problem I will be doing later on, I will give the value of saturation temperature, also the liquid surface temperature. Generally this is something you can calculate using humidification, okay. Since we have not covered that, we will give you these values, okay. But from the concept point of view, we say that during this drying process, the heat is transferred from the gas to the liquid, and the liquid is evaporating by consuming that heat via latent heat. And this process can reach a steady state. At that steady state, the liquid temperature will take a steady value. Corresponding to that liquid surface temperature, there is a saturation humidity that we can find. Now that saturation humidity minus the actual humidity is a driving force for the drying to happen, okay. So these are all the important things to remember. Now if you consider this expression, again we are talking about a solid having a thin film of water covering it, and this humidity is constant because we say constant drying condition. The air is coming over with the same humidity over and over, okay. So humidity is constant, its inlet temperature is constant, and the surface temperature of the liquid is also constant, meaning Ys is also constant and Ky is also constant. So this all will tell you that there is a particular scenario where the mass transfer flux will be constant, okay, because all the quantity that I am involved here can be treated constant for certain conditions as long as there is enough moisture on the surface, okay. And that is what you see here, that the reason for having a constant drying rate is because you are talking about here a drying of a unbound moisture, okay, exerting a vapor pressure equal to the pure water, and here the mass transfer rate is limited by the gas phase. And then if you write the expression for gas phase mass transfer, all the quantities involved, the driving force, the mass transfer coefficients, these are all constant. So you can say that the constant drying rate period that you see here is characteristic of a drying of an unbound moisture. So we say Ky is constant because the gas flow conditions are constant. We say Ys is also constant because the heat and mass transfer rates are balanced, and the liquid temperature is constant, and the humidity of air is also constant. So, because of this we say this NC, we will say C means constant here. Okay. So, we can understand that this particular part is related to drying of an unbounded water. Then what happens after that? You can still have drying continuing, and then once you have dried enough moisture, the surface would form some dry spots because the thin film is getting evaporated, and then you will have few pockets of dry spots on the surface of the solid. Okay. Still, I mean, if I have to draw pictorially, let us say you start with some sort of solid containing a thin film of moisture, okay, and this dries, and then at some point of time what will happen is you will see some sort of hole formation, dry spots are formed. So, this is a dry spot here, these are all dry spots, because at some point of time water is leaving, so it will expose the dry surface. But the original N, that mass transfer rate, is written with respect to the initial overall wetted area. Okay. But here once you reach this point, drying is happening only from those film area, which is much lesser than the overall initial wet area. Because of this, N will keep decreasing. Okay. That is why we call this falling rate, this rate C to D, we call it as a surface drying. Still moisture, unbound moisture is present on the surface, but this is only because of change in the area of drying. And then once this happens, okay, this is called surface drying, and this is because of change in the, because of this hot spots happening, I mean the dry spots happening on the surface, and N is defined based on the original wetted area. So, this change that you see here is mainly because of change in the available area for drying. And then after some time what will happen, even all the other film will also completely dry, the entire surface, outer surface is now dry. Now, if it still has to dry, moisture will have to come from the interior to the surface, right. Now, I already said the moisture content inside the body are called bound moisture, and the bound moistures are kept inside the capillaries, inside the microstructures, due to strong interaction between the water and the interior surface, and that water will have to come out. Okay. So, then we are talking about mass transfer rate limited by the internal diffusion of water from the interior to the surface. Okay. And that is what this we say as a drying of internal moisture. Okay. So, therefore, we say that there is a constant rate drying and there is a falling rate drying. Within the falling rate drying, there is a two mode. One is this surface drying, and the other one is internal moisture or bound moisture drying. Okay. And how long this can go? This can go only up to some equilibrium moisture content, and this equilibrium moisture content also depends on the drying condition. Suppose if I change the air to very high temperature or very low initial humidity, this drying can also happen to be somewhere here also. Okay. Let me also draw your attention to the previous plot I showed you, where we showed the relationship between the humidity of the drying air and the equilibrium humidity. Okay. So, this corresponds to one equilibrium humidity. If I change the drying conditions, I can go to different equilibrium moisture. So, this plot has to be understood together with this plot. So, this equilibrium moisture can be changed by changing the drying conditions, but once you fix the drying condition, you will always see that it will come to some equilibrium moisture content. Okay. So, if you look at this, then we see that the so simple looking drying curve here has many physical mechanism of drying related to constant drying and falling rate drying, and within this we have surface drying and internal moisture drying. There is also some small initial part which may or may not present for different materials. This is called initial transient or initial adjustment, because I said that during the constant drying, the liquid temperature takes a constant temperature because of the balance of heat and mass transfer. Corresponding to that steady state temperature, if the initial temperature is different, okay, so there will be a small amount of initial change in the rate of drying before it reaches a constant drying. So this is called initial period. This time that takes to come to the constant rate drying is so small, many times we actually even just ignore this point. Sometimes you may not even see that, because the time scale to develop that stage is so short, you may not even see it. Okay, so these are main features of drying. Involves initial adjustment, constant rate drying, falling rate drying. Within that falling rate drying, we have surface drying and internal moisture drying, finally leading to equilibrium moisture content. Okay, majority of the material that we do drying will show this kind of characteristic curves. So with this, now what we can do, we can actually now develop expressions for time of drying based on which mode we are going to dry. Time of drying. Let's say I am looking at moisture content removal in the constant rate. Okay, so constant rate drying, where n is equal to nc for x less than x greater than xc, where this xc is the critical moisture content. So you can see this in this figure, the critical moisture content is somewhere here. Okay, the one where the switch between constant to falling rate happens, that is called the critical moisture content, corresponding to this point. So let's say we are looking at drying in this particular range somewhere. Okay, we want to reduce the moisture from one level to the other level, but during that operation, let's say the rate is constant. Okay, if that's the case, getting the time of drying is so easy, because we go to the definition of n, which is minus ss by a dx by d theta. I am writing in now differential instead of delta, and here n is equal to nc, because it is a constant rate of drying. So from here I can rewrite this equation, d theta is equal to minus ss by a dx, and nc also is here. A simple integration basically gives you the time required to dry a material from x1 to x2 under constant drying conditions. This constant drying condition NC will have to be obtained from experimental batch drying data. So once we do one experiment and then we produce this kind of drying rate curve, that can be used for different kinds of, as far as the drying conditions are concerned, let's say you want to dry for different moisture contents, you can use this data. Okay, that's how we take data from a laboratory data and then use it for estimating time of drying under different moisture contents, as long as you remain in the constant drying rate. Now the second possibility is drying under falling rate regime. Falling rate regime. So that means we are talking about X less than the critical moisture content. So from this definition, So in the falling rate regime, the drying rate n depends on the moisture. So that's why I keep this n inside the integral. Okay, so this is something you can do graphically. So we plot 1 by n versus x between x2 to x1, and then we get the area under the curve. Okay, so that should give you the time for falling rate drying. Now suppose if you are lucky and the falling rate follows a linear straight line, we can also try to get this analytically done instead of graphically. Okay, so let's say in the falling rate we find that n is given as something like mx plus b. Okay, need not be the case, but need not always be the case, but in some drying tests we see that the falling rate drying rate can be given as a linear equation. And so now we can go back and then substitute here. So we get x2 to x1 dx by mx plus b. Okay, so this is a capital X. There should be an m here. Yeah, right. So here what I have done is I have assumed that the falling drying rate is assumed to be a linear line, and then I substitute that in this integral, integrate it, and we can stop here, but we can also do a little bit differently here. We can write that this term mx1 plus b is nothing but n1, and mx2 plus b is n2. Between these two equations I can write m, the slope of the line m, in terms of n1 and n2 and x1 and x2, and I can substitute this m in this equation, and when we do that we are able to recast this equation in a simpler form, which involves logarithmic mean difference of the drying rate n1 and n2. Okay. And you can see, if you compare this equation which we have written for drying rate with the constant drying rate, we have theta equal to ss by a x1 minus x2 by nc. All you need to do is replace this nc with logarithmic mean difference of n between those two, n1 and n2. Okay. So writing this equation is somewhat convenient, because if I know for constant rate, from here I can directly write in this form, because the forms are very different. We are replacing the constant rate with the logarithmic mean difference of the drying rate. Okay, so that's the advantage of this particular form. So instead of writing n is equal to mx plus b, you can also choose to write mx minus mx star. So what this means is you have a drying curve where you have a constant drying NC up to some critical moisture content XC, and then till this equilibrium moisture content, if this is a straight line. So that means I am thinking about the falling rate as a one single phase. I am not distinguishing between the surface drying and internal moisture drying. The entire falling rate can be assumed to be a straight line. So then this drying curve is constant up to it falls linearly up to some equilibrium moisture content x star. So then I can write the falling rate falling rate as m times x minus x star. So all that we are doing is we are saying this constant b is nothing but minus mx star. Okay, so with this you can rederive this, and I'll give the final equation. It's something you can test this out. You will get SS by A NC And the reason why we get this term NC here is because when we eliminate this slope of this line, that would actually involve NC also. Okay, so that's how this NC is coming in here. And this is this is something that you can directly derive from basically follow these steps. Instead of B, you're going to substitute minus mx star. Okay, and then you're going to eliminate m using NC minus 0 and x1 minus x2, and if you substitute that, you'll get a final answer. So only thing you have to be very careful is this equation you can only use if you have a falling rate linearly varying up to equilibrium moisture content x star. Okay, only then this is applicable. Whereas this one can be applicable between anywhere x1 and x2, need not be all the way to equilibrium moisture content. Okay, so I'll stop here, and the next class I'll do some problems on this constant drying and falling rate drying.